Hello, pre-calc students. This is Mr. Beck. Today we're going to be talking about Chapter 5, 5.1, 5.2. 5.1 is composition of functions, and 5.2 is going to be one-to-one functions and inverses of functions. So to begin, just take a little recap of where we've been. Chapter 1, we found different properties of equations, zeros, intercepts, etc. Chapter 2, 2.1 specifically, we began focusing on domain of functions. 2.4, we talked about transformations and what some of the basic pair functions look like. Carried on and built some equations. Chapter 3, we focused specifically on two specific functions, the linear function and the quadratic function. Chapter 4, we were talking specifically about polynomials and rational functions. Here in Chapter 5, our focus is going to be on exponential functions and logarithmic functions. Before we get into that, we need to talk about some of those functions, especially exponentials and logarithms are inverses of each other, which is why we're going into 5.2. So let's begin. We're going to discuss what is the composition of a function. Very simply, a composition of function is one function that is inside of another. I prefer to use this kind of notation for it, but a lot of times we will say FOG, often called FOG. So FOG of X is F of G of X. I'll continue with the FOG notation just because it's something our book uses, but you'll see that I switch back and forth pretty interchangeably. So G of X is going to be the inner function. So as I look here, I specifically see that we have two distinct functions. What I have in red here is the quadratic. And what I am about to put in a greenish color is going to be our fifth degree polynomial. So we really have a quadratic stuck inside of a fifth degree polynomial. The inner function is going to be g of x. The outer function is going to be what we're calling f of x. So looking at functions this way it's a change in how we approach it, because a lot of times you see, oh, that's an equation. That's the equation that's given to me. What do I do with it? From here on out, it's can you recognize functions that you know and compare them to say, okay, this function is inside this function, so on. Anyway, let's get into it. So what I have in blue here, it specifically says that I'm going to be taking f of x, and I ask this question a lot, why is this an x right here? Why is this blue an x? Well, it's an x because what's inside the parentheses here is an x, because the function says, all right, f of something is going to be 4 times that something minus 2. And you see, like, a lot of times we'll say, oh, f of 3 in this case is 10. If f of 3 is 10, great. But then this question, what is f of a square? Well, the function knows that it takes 4 times the square minus 2. This has no meaning to us. However, the function is doing its job. It's taking whatever's inside the parentheses and it's saying, okay, 4 times that minus 2. So when we have a composition of functions, if I'm saying f of g of x, what's really happening is we are putting that g function inside the f function, so it's going to be 4 times that g function minus 2. A lot of times we'll see it written this way as well. Once again, I kind of do it interchangeably just based off of what I see in the moment. But we can approach this either way. We can either say 4 times g of x minus 2 and then substitute x squared minus x minus 1 in for g at that moment. Or we could just right from the beginning just say, oh, this is what g of x is, and then plug it in. And then once you plug it in, we definitely want to simplify. So on part B, this is f of g of negative 1. So we could do this one in two ways. One, we could find g of negative 1. And then once we know g of negative 1, we can then take that g of negative 1 and plug it in for g of negative 1 there. And find f of 1, 4 times 1 minus 2, which is 2. Or we could sit here and take the expression that we found, which is probably going to be a better approach now that we've already established we have this whole expression. Let's just plug negative 1 in here. If we plug in negative 1 here, that would be 4 times negative 1 squared minus 4 times negative 1 minus 6. So 4 plus 4 minus 6 is 2 one more time. For this problem, g of f of x. So for g of f of x, what it is we need to do, we need to take that f function, square it, subtract it, and then minus 1. So you see the work that I have here. We have 4x minus 2 squared. Don't forget to FOIL that. Don't forget to distribute the negative, and then simplify to 16x squared minus 20x plus 5. And at this point, I'm going to go ahead and just plug in the 4. G of f of 4 gives me 181. Same thing for this problem. Now this is definitely a little bit more complicated because we're going to have a trinomial squared. So when we square the trinomial, don't forget, I tend to line up all of my common terms. That way I can just add them together. And so we get that by x squared times x squared times negative x squared times negative 1. So it's a long distribution process. But anyway, plug it in, that's what we get. Now g of 2, g of 2 is negative 1. We could find it by plugging it in here. Or in this case, it might actually be simpler just to plug 2 into the g function. So if we plug 2 into the g function, we'll get 4 minus 2 minus 1, which is 1. Then plug in 1, we'll get 1 minus 1, which is negative 1. So this is definitely a case where g of 2, so g of 2, if I said g of 2, g of 1, which is negative 1, I think that one might actually be a little faster to do numerically. Now, I said numerically, we did this algebraically, but if we do it algebraically, we could also have a graphical representation. Something I just threw on here right at the very end. I took a picture of something in the book, and I said, hey, what is f of g of 1? We know that g of 1, g is the upper function, so g of 1 is 4, and now we'll say, what is f of 4? 0. The other one I just randomly chose, and I'll do this in highlight, g of 6. So g of 6, that's not the g function. How about g of 6 is 5. Now it's g of 5, 4. We could do this with anything. But anyway, so we have algebraic, we have graphical, and then this table means we can do it numerically. So if I want f of g of negative 1, I first want to find g of negative 1, and I do that in the blue highlighter right here. G of negative 1 is 0, and now f of 0, I have that in the red highlighter. It would be negative 1. Same thing, first find f of negative 1. F of negative 1 as I go to my chart. F of negative 1 is negative 3. Now I want g of negative 3, which is 8. F of negative 1, so f of negative 1 is negative 3. And then I want to find f of negative 3, which ends up being negative 7. Or g of negative 1. G of negative 1 is 0. And now I want to know what g of 0 is, which is negative 2. So I apologize for that. You probably didn't realize I just had a brief interruption. We're at an impromptu Zoom meeting, but that's okay. Where we were discussing the composition of these functions. When it comes to B, C, and D, we do a lot of the same thing as what we did with part A, which I remember we talked about. Now, big question is, can we do all of these functions? If you notice that I did introduce a new problem, f of g of negative 3. So if I ask for what is g of negative 3, g of negative 3 is 8. Well, then what is f of 8? I don't have an f of 8 because it's not in my column. Therefore, it does not exist, or it's undefined. Undefined is probably a better terminology for this right now. But it is not possible for us to be able to find that. So this level 4 problem, which I'm going to argue this one really is not a level 4 problem, where it's to identify if we are given an expression, what is the inner function, what is the outer function. The most common answer to this is we see that we have a cube root function, and that cube root function then would be the outer function. That would be our f of x right here. And then the inner function is going to be that quadratic. Now, my challenge to my students, and why I have this on the notes, is can we come up with any other variances of this so it's not just the normal average everyday one. The first one that naturally comes up for me is what happens if I say, okay, I'm going to take these cube root of something minus 3, which then I can write that as my outer function, and my inner function is just going to be that 4x squared plus 6x. And then again, these are two just different variances of it. If I take a look and break it apart like I did, break that quadratic up like I did up at the top, then that third option is going to be viable. And I did have a smart aleck student who said, hey, can't this work? And yes, that student was actually right. So, lots of different ways we could do this, but it's kind of like it's an open-ended question, so it's not just one specific answer. Moving right along. Next problem, what is f of x? So we ended up making it a more and more complicated problem, so which is great. I enjoy it. So the first thing I did is what I have in red. It's the f of x first. So with f of x, I plug in the f function into the f function. So that is inside of 1 over 1 minus x. So then strategy that I have for a lot of you, and I know I've mentioned this in previous notes, but multiply by that denominator. So multiply this overall fraction by the denominator. What that does is this will distribute to the numerator, so I just have 1 minus x. This will distribute to each term in the denominator. So 1 minus x times 1 is 1 minus x. 1 minus x times 1 over 1 minus x is just 1. And then simplify to this expression. And now I need to take f of that. So to take f of that, I'm going to go ahead and plug it in right here. And then I simplified to this part of the expression. Now that I'm simplified, then I'm going to multiply by x over x. If I multiply by x over x, once again, it clears your fractions. X times 1 is just x. X times both terms would be x plus, and then here's where the x's are going to cancel, x plus 1 minus x, which simplifies just down to x. So this is kind of great, because what this means is whatever I plug into the original f of f of f of x is what I should end up getting out. So if I do that with 3, I will get 1 over 1 minus 3, so I'll get negative 1 half. If I plug in negative 1 half, then I will get 1 over 3 halves. And if I plug in 3 halves, then I will get 1 over, sorry, I just lost my train of thought. I'll get 3. Now, if I try to plug in 1, so f of 1 would then give me an undefined value. So this actually does have some limitations that we weren't prepared for. The limitation that we weren't prepared for was, well, why can't x equal 1? Well, x can't equal 1 because then it makes your original function undefined. So even though this simplifies, we have to keep x is not able to equal 1 because that maintains the domain of the original function. If I tried f of 0 is 1 over 1 minus 0, so f of 0 is 1. And then what is that f of 1? Well, now we hit an undefined point too. So I have 2 overall domain restrictions here that I wasn't necessarily prepared for, but they still exist. So one of the things that we have to look at is, okay, yes, we get an expression, but how does that expression simplify? And what's going to be the fastest approach? Well, what I did was I took a look and said, okay, what can x naught originally be? And then as I did my f of x, did it come up with any new domain restrictions? And then if I did f of x, did it come up with any new domain restrictions? So you kind of look at domain restrictions every step along the way to see if we end up encountering any of them. So that is the overall approach that we are going to take to domain of a constant function. First, we find the domain of the inner function, and then find the domain of the result, and we take a look and intersect both of those domains. So if you look at what I have here, so my inner function is going to be g of x. The domain of that is going to be negative infinity to infinity because it's a line. Now, when I do my substitution, if I plug this in for x right here, then I will get the square root of 2 minus x. And the square root of 2 minus x, if you remember how we do domain with that, then we set that greater than or equal to 0, and we get x is greater than or equal to 3. And so it's at this point that I'm going to say, okay, what is that domain and that domain intersected? So x is greater than or equal to 3, and all reals just turns into x is greater than or equal to 3. For part B, start off with the domain of the inner function. Domain of the inner function, this is kind of some chapter 4 review for us. So I have this expression 3 over x has to be greater than 0 because what's underneath the radical must be greater than or equal to 0. I'm going to go ahead and put that or equal to 0. So if you remember with rational inequalities, what we did was we took a look at where do we have zeros or undefineds. In this problem, I only have one undefined function or one undefined value. And then you test all the regions to determine what are the signs in those regions. And so the domain of the inner function is just the positive numbers. Then when I do my composition, plug in the square root, and this is just to be a little bit more specific, the square root squared ends up into the absolute value. That's really your definition or your mathematical definition of absolute value. So the domain of that is everything but 0. And so the intersection of everything but 0 and all the values greater than 0 is going to be just all the values greater than 0. For our level 3 problem, the domain of my inner function, x just has to be positive, or sorry, x is not allowed to be 0, which is what I have here. Then if I do my composition, plug in g of x in here, once again, multiply by the LCD over the LCD, and I end up with this expression, which now my denominator is not allowed to equal 0, which is why x cannot equal -3/2. So the intersection of x can equal -3/2 and x cannot equal 0 is the expressions that I have done. On to part B, x is not allowed to equal -1. Do my composition, and then this one is let's multiply by the reciprocal. So now I would say x plus 1, and to be a little bit more official, 2/3 times x plus 1 has to be greater than or equal to 0. So x is greater than or equal to -1. And if x is greater than or equal to -1, we intersect that domain with that domain, we get just only the values greater than -1. So 5.2, this is where we talk about one-to-one and inverse functions. And the idea behind a one-to-one function is every x has its own unique y, which if you see what I have boxed over here, this is the case where this x has its own y, this x has its own y, this x has its own y. But so that is a one-to-one function. Now, this first example is a function, but it's not one-to-one because we have x's that share a y. That second case is not a function. Since it's not a function, it can't be a one-to-one function either. So graphically what happens is this means that it's going to pass the vertical line test and the horizontal line test. So if we take a look at this first situation, if I know that I have, let's just say a parabola, because parabolas are great functions, but they don't have inverses because this y comes from two distinct x values. So not a one-to-one function. Anyway, is this following relation a function? Yes, it is. It's a function because each x gets mapped to a different y. Sorry, I shouldn't say it that way. Each x goes to a y. So an x does not go to two different y values. It's not one-to-one because we see, oops, wrong tool. We see this situation right here where we have two different x's mapping to the same y. So one of the questions I used to ask my Algebra 2 students is, hey, how can we change this problem so that it is now a one-to-one function? I just had a student, I asked this last period, I had a student said, hey, let's go ahead and change that 6138 to 6139. As long as that number is not 38, we're in good shape. Now it's a one-to-one function. It can't be 38, 34, 54, or 57. With inverse functions, this was kind of a little exploratory problem where I'm given a function, and the function really is only the points. It's a lot harder to see the relationship fully without like connecting them. But if we have a function to find its inverse, what we do is we switch our x and our y coordinates, and it's really that simple, switch the x's and y's. Then to find the domain of the function, we just choose the x values. To find the range of the function, we find the y values. So these are all the y values that come from f. These are all the y values that come from f inverse. These are all the x values from f, all the x values from f inverse. Now what you should notice is, and this is true of all functions, that the domain becomes the range and the range becomes the domain. If that doesn't happen, something went wrong and we have to account for it. Then the relationship between these two functions is that it's a reflection over the line y equals x. And the reason why it's over y equals x is because x's and y's get switched. Now to find the inverse algebraically, what we do is we switch x and y and solve for y. So in this first case, we have a linear function. So our most basic case, linear function, switch x and y and solve for y. Now, please note that in the directions, I'm always going to ask you to find f inverse of x. So if you do not leave your answer as f inverse of x, then you're going to lose a point. And I would hate to do that when you knew how to find the inverse. Now it's about calling it what it is, not just saying generically y. We like to have it named properly because then it shows it does come from another function. It's connected to that other function, and it allows us to make those stronger connections in general. For me, it's okay if you leave your answer in any of the forms. X plus 7 over 2 would work. Half times x plus 7. There's even the option of saying 1/2 x plus 7 halves. So as long as your expression is correct, I will accept it. For part B, I usually catch students on this one because there's something that's important to know. That part B, f of x is the square root of x plus 1. Yes, we could find our inverse. Our inverse ends up being a quadratic. Now, the big idea behind this inverse being a quadratic, we started off with a square root function, which looks like so. The inverse is a quadratic, but the full reflection over the line y equals x is going to look more like this. So we only want the positive half of the quadratic. So as we're going to find the domain of the inverse function, we do need to keep the original range in mind as we find the domain of the inverse. And now graphically, this is a shift down one, which is why our range goes from -1 to infinity. I have a lot of students say, how was I supposed to find the range of this original function? This is where, let's go back to our chapter 2.5 or 2.4, where we talked about the parent functions. This is the square root function shifted right one. Sorry, left one. I'm speaking too quickly. For our level 2 problem, one of the big things that this was just to see if I could catch any students to say, hey, this is not one-to-one. Since this is not one-to-one, we have issues. The way our book will address these issues is we know that this is not a one-to-one function, so they will initiate, and I'm going to stress, they will initiate a established domain, so we do have a one-to-one function. So with this problem, I'm going to establish the domain x is less than or equal to 0. And I'm doing this because our book does not. And this is an important concept. You'll see as I work through the problem or I talk through the problem that this is an important concept. The book will only establish positive domains. I'm establishing a negative domain because I want to show you something. And oh, by the way, I'm going to be testing this idea, so please make sure you pay attention. The fact that x is less than or equal to 0 means that we are going to have this half of the parabola. It's the negative half of the parabola. When we switch x and y and solve for y, we have to take the square root of both sides. And when you take the square root, you're going to introduce both a positive and a negative. By introducing both a positive and a negative, we're now saying that we are not going to have a function because we have two different components to it. We want the negative square root because we had started off with the negative half of the parabola. If we had started off with the positive half of the parabola like your book does, we would want to end up with the positive square root. So please be careful about that. As I said, I'm going to be testing it specifically because it shows that you're understanding the connection. And it's a graphical connection. For part B, switch x and y and solve for y. Looks to me like I did not actually write the domain of this. So the domain of f, I know that this is a rational function. This is great practice for the chapter 4 test that's coming up. So this is a rational function. The domain x is not allowed to equal 5 because it makes the denominator 0. Now this is a proper rational function, so that this also has a vertical asymptote a horizontal asymptote at y equals 0. And we know this is kind of a simple case, so I believe this graph actually looks like this. So we are not going to cross the horizontal asymptote, meaning y is not allowed to equal 0. Now we switch x and y and solve for y, and what you should see here is f inverse of x equals this expression. We can go to that expression and say the domain of the inverse function, x is not allowed to equal 0. And the range of the inverse function, since the coefficients are since they're both linear, they have the same degree, we can take a ratio of the coefficients to say y is not allowed to equal 5. And if you notice, x's becomes y's and the y's became x's. For our level 3 problem, same thing, x is not allowed to equal -2. Looking at the ratio, y is not allowed to equal 1. Then to switch x and y and solve for y, something special happens here, and we have a y in 2 different locations. That y in 2 different locations means we're going to have to multiply both sides by y plus 2. And then I'm going to first get rid of those, but then what I was saying is we have 2 different y's. This y and this y are on opposite sides of the equation when we multiply by the LCD. What we need to do then is combine them onto one side, factor out the y, and by factoring out the y, now we can get y by itself through division. So f inverse of x is going to be -2x minus 4 over x So x is not allowed to equal -2 because it makes the denominator 0. Y is not allowed to equal 1 because of the horizontal asymptote. Starting from the bottom, x is not allowed to equal 1 because it makes the denominator 0, and y is not allowed to equal -2 because of the horizontal asymptote and the ratio of those coefficients. Moving on to part B, same thing, but like I said, or like I did before, I didn't actually include the domain and range of these functions. So let's look at f, the domain of f. X is not allowed to equal -3. The range of f, y is not allowed to equal -3/2 because of the ratio of those coefficients. As we do the algebra one more time, switch x and y. Now when we solve for y, we have to multiply both sides by 2y plus 6, which then gets rid of the fractions. Combine the y's together on one side and factor it out, and divide. So once we divide, here's my f inverse. X is not allowed to equal -3/2, and that's because it makes the denominator 0. What I did was I set the denominator equal to 0, so 2x plus 3 is not allowed to equal 0. So x is not allowed to equal -3/2. So our domain of f inverse. So the domain of f inverse is going to be x is not allowed to equal -3/2. And then if we take a look at the ratio of those coefficients, y is not allowed to equal -3, which flips those around. Last but not least, to verify functions are inverses. If they are inverses, the two functions undo each other. So if I plug into 5, I do the function on it, and then I do the inverse function, I should end up with that same 5. Now, I am requiring you to do this algebraically. To do this algebraically, your goal is to plug in f of f inverse, and in the end, your expression should simplify just down to x. So if I plug in f inverse, and I'm plugging in f inverse into the f function, and this is referring back to problem 3, the f function is x minus 4 over x plus 2. But instead of x, I'm plugging in f inverse. Multiply by the LCD, you can see that x minus 1 distributes to the first term, distributes to the second term, distributes to the first term, distributes to the second term, which simplifies down to x like it was supposed to. But we don't just stop at doing one side, we have to work backwards, f inverse of f. So we are going to take f, and f is now going to become the inside function. We're going to do f inverse that we found right up there. So -2 times that x minus 4 over that x minus 1. This time we're going to multiply by the LCD of x plus 2 over x plus 2, and distribute, 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 and simplify, we get x again. So that is all that I have for you. I hope that you have an amazing weekend. Bye, guys.